Hey there, Mr. Loma here. I thought I'd do a quick video about implicit derivatives for you. Hopefully this helps a little bit in your studying. And it's one of the most powerful techniques in all of calculus, and it's really quite shocking when you think about it. First of all, let's suppose we were trying to find the slope of the tangent to the circle x squared plus y squared equals 25 at the point 3, 4. The first thing to notice is the circle is not a function. So if you thought that you could do calculus with only functions, you were wrong because it's so powerful you can do calculus on things that are not even functions. As you can see, it fails the vertical line test. Anyway, so what we want to do is we want to take at the point 3, 4, we want to draw a tangent here, and we want to find the slope of that tangent. So let's go ahead and do that. Okay, so there we go. We have our tangent drawn, and we want to know the slope of the tangent of the blue line. Now, sometimes we have very clever people in our class that notice that there are some things you can do. We don't do enough geometry anymore, but if we were to draw a radius straight across from here to here, that might actually tell us something. So let's go ahead and do that. Okay, so we've got the radius drawn in there. I think everybody can see that the slope of the green line, I'm going to try and draw it down here out of the way, is up 4 and over 3. So the slope of this line is 4/3. So the slope of the blue line, which is perpendicular to the green line, must be the negative reciprocal, which is -3/4. And we're done and the lesson's over. No, just kidding. 99% of my students will not see that. Um, so we have to come up with another method. Besides that, this only works for this particular circle, and we're going to deal with any kind of relationship. Doesn't have to be a function at all. It could be a crazy spirally graphy thing and it'll still work. So option number 2. Most of the time I have a student say to me, Mr. Loma, this function is not written explicitly in terms of y. In other words, it's not written y equals, but we could put it in terms of y equals by subtracting x squared and square rooting both sides. And a note here, you cannot simplify this to 5 minus x. Don't do that. That's bad. Very sad face if you do that. Trust me, you can check it off to the side if you want. That is not legal. All right, so what have we got here? Well, we actually have 2 halves of the circle. The part that we're going to be using is the top half, which is y equals the square root of 25 minus x squared, which is actually the top half, which looks like that. Okay. Try graphing it on Desmos if you don't believe me. And now what we can do is we can take the derivative, and just to be clear, we have y explicitly written in terms of x, so we can do the derivative straight away. So 25 minus x squared, recall, is 25 minus x squared to the half. So the derivative is 1/2. Leave the bracket completely untouched to the negative a half, because you got to reduce the exponent by 1, times negative 2x. Now this part can get a little bit touchy here if you're not good with exponents and fractions. When you have a negative a half on the exponent, hopefully you can see my cursor. I'm not 100% sure that you can, but hopefully you can. The negative sends it to the bottom, so it's going to be 1 over, and the half means you root it. So 25 minus x squared, and then you have negative 2x. And if you put all this together, you get negative 2x on the top, 2 root 25 minus x squared on the bottom, and an astute observer would notice that we could get rid of the 2's altogether. In fact, I'm not going to bother writing 1 either. It's just going to be negative x over the square root of 25 minus x squared. And that is the derivative, and it's true all the time. Just clean that up a little bit. Yeah, so that gives us derivative all the time. And at x equal to 3, which is the point we're looking for, the derivative will be negative 3 over root 25 minus 3 squared. 25 minus 3 squared is 16. And when you square root it, you get 4. And you get negative 3/4 as we expected, because that's what we had there, and that's what we had there. So that's method number 2. A little bit ugly, as some people would say, and we had to rearrange it for y. Now what I will tell you is that sometimes you can't rearrange it in terms of y. And so this method will not work. You could have a y squared term and a y cubed term. You could have a y that's stuck inside a sine or a cos or a log. And so we can't just rearrange it. In this case, we could. There was only one y, and we could isolate it. So we're going to have to come up with another method. And that's where this wonderful thing called implicit derivatives comes in. So here's what we're going to do. We're going to just go on a very quick side trip to remind you that if we had y equals x squared plus 1 to the 7, the derivative of that would be 7 x squared plus 1 to the 6, and then you would have to put on a chain rule to correct it. And basically what that means is any time that you take the derivative of something that is not an x and you pretend that it is, you have to take the derivative of that thing in order to, quote, correct it. Okay? So what I want you to do is see if you can follow along with this logic. What if I said y equals a to the 7th, and I asked you to find dy dx? Well, as we saw previously, when you try and do the derivative of y, it only has a's in it, so what you do when life gives you lemons, you just do the derivative with respect to a, because that's what you have, as long as you, quote, correct it by doing the derivative of a with respect to x. And so that's what we do. And you see how it's chained here, like completes the chain. Now dy dA is a very easy derivative. That's 7a to the 6th. That's very nicely done. And dA dx is what you have to correct it by. And I'm not sure if you can see this, but if you were to let a equal to x squared plus 1, you could see how this work up above is exactly what we did here. So 7a to the 6th, that's 7a to the 6th right there. And 2x is the chain rule, or the derivative of x squared plus 1, which is a. So derivative of a with respect to x, which is just 2x. So you can hopefully see, and I'll write it here just to clarify, if a is x squared plus 1, we can just replace a with x squared plus 1. And the derivative of this is just 2x. And that goes at the end, dA dx. So hopefully you can see how that chain rule is working there. And all that really matters is that you remember that whenever you take the derivative of something that is in terms of the wrong variable, you have to correct it using this wonderful thing known as the chain rule. So where am I going with this? Well, it turns out, just like you could square root both sides or add 5 to both sides of an equation or log both sides or do the inverse cos of both sides, you can also take the derivative of both sides of an equation and we say with respect to x, because x is the variable that we're dealing with, and this is completely legal, which is beautiful. So what I'm going to do is switch colors here so you can see what's going on. We're going to take the derivative of 25 with respect to x. That's just 0. The derivative of x squared, it's in terms of x. It's beautiful. It's just 2x. But here's where it gets interesting. The derivative of y squared with respect to x, you can't do it. So what you're going to have to do is you're going to have to do the derivative of y squared with respect to y, because that's what you have. So that's just 2y. But then you got to correct it. Since you pretended the y was an x, now you got to differentiate y with respect to x. And the good news is, better use a different color here. This is exactly what we're trying to find right here. Let's see. This is the derivative we're trying to find here. And so you might ask, well, what good did that do? Well, we just found our first derivative implicitly. So we're going to move the 2x over there. We're going to divide by 2y. And we could simplify it, not necessary, but we will. And this, my friends, is the derivative everywhere, just like we had up here. And if you look at negative x over this thing, we have negative x over y, but y is equal to square root of 25 minus x squared. So we actually do have the exact same answer. And I'm going to recommend just leaving the y in there. Just remember, when you're trying to evaluate this at a certain point, you might have to find the x and the y coordinates. When x equals 3 and y equals 4, so now we have both variables, you just sub them both into the equation. You get negative 3 on the top and 4 on the bottom. And once again, I'm going to grab my yellow highlighter and show you that the 3/4 is the same 3/4 we got up here, and also the same 3/4 we got up at the top here. And that's our first implicit derivative. Now it does get a little bit harder, and since the video is getting a bit long, I'm going to stop there and then put a example in a different video. Anyways, I hope that helped, and we will talk to you soon.